Cathode ray tube screens are quite bulky and nearly the oldest of all moving picture screens. This display uses phosphor, a powdery substance that reacts to electrons to create an image. This substance is sandwiched between two panes of glass in front of the display. Full-colour CRT screens use red, green and blue phosphor, organised into a little block that we now call pixels. Behind this is a component similar to a flashlight that is aiming a beam of light at the phosphor. However, it isn't light at all, it just looks very similar to light. This beam, rather, is of electrons. You can tell the difference between the two because magnets are able to push and pull this beam of electron energy. This beam is pushed and pulled left and right, up and down, with horizontal and vertical deflection plates at a rate such as 30 times per second to temporarily light up the phosphor in certain amounts. The phosphor remains illuminated even after the electron beam has moved on to the next pixel, but only for a limited amount of time. This is where we get the name electronics. We're always controlling the flow of electrons with computer technology. The liquid crystal display uses a substance that is either a liquid or somewhat of a solid depending on its temperature, and its solid state is referred to as a crystal due to its structure. Temperatures under 32 degrees Fahrenheit can damage an LCD screen. The actual liquid crystal in a computer or television screen is sandwiched between glass and two layers of light polarizing filters. Polarizing filters only allow certain wavelengths of light through them, according to the orientation of the filter. The liquid crystal layer reacts to electricity in ways that allow light to pass through it in controlled amounts, resulting in different amounts of brightness on the other side. Although liquid crystal itself can have color-changing properties in a screen, it is only used transparently to control the waves of light that pass through it. As you can see on the left, a polarizing filter has blocked certain wavelengths of light that aren't orientated in a way that can pass through it. On the right, nothing is blocking those wavelengths. An LCD uses a color filter consisting of an RGB grid on top of an LCD layer, and beneath a second polarizing filter that cancels out the remaining unwanted light. Only specific amounts of light are let through in specific spots. Pixels. If you're still confused, think of a fence that only allows vertical beams of light through its gaps. Both polarizing filter layers and the liquid crystal layer in between have defined gaps for specific waves of light, but only the liquid crystal can be manipulated on demand using electricity. The polarizing filters have their gaps defined beforehand and are installed with different orientations. Light is able to pass through only if the liquid crystal has an electric current manipulating it in a way that permits it. Ultimately, all three layers control light in very specific tunnels for each pixel subpixel. The light-emitting diode screen is just like an LCD screen, but instead of a cold cathode fluorescent backlight, which is a series of fluorescent lamp bars, it uses individually lit bulbs. The number of LEDs in each screen varies, with some containing a full array, some only a handful of evenly distributed bulbs, and some lighting up only the edges of the screen. These diodes can improve brightness, power, efficiency, and reduce the weight of the display, but for the most part, LEDs are the same as LCDs. The plasma display has characteristics of both the cathode ray tube screen and the LCD screen. Each pixel block is filled with tiny amounts of the gases, neon and xenon, mixed together, and this gas emits a light when electrically charged that interacts with phosphor to create an image. So it utilizes phosphor like a CRT, but instead of an electron beam, it uses electrically conductive and magnetic grid layers between glass panels like an LCD. Like CRT displays, plasma televisions are susceptible to burn-in. This is when an image remains on screen long after voltage has stopped being applied, usually due to an overabundance of use. Liquid crystal displays have a similar issue, but the burn-in isn't permanent, and so it's simply called image persistence. Plasma televisions have wider viewing angles than LCDs, but the brightness in a plasma television can wear out as phosphors will eventually lose their luminescence, just as in a CRT. Plasma displays stopped being produced and sold around 2015 in favour of cheaper, more energy efficient and thinner displays. like LCDs. Organic light emitting diode displays, or OLEDs, do not use a backlight. Rather, each pixel is individually controlled with electrically lighting up electrons in specific areas to produce light. The actual layer emitting the light is complicated and varies across different OLEDs, but it's similar to thin aluminium or silver, is lightweight, durable, and is very complicated to make. OLEDs have among the highest rated picture quality of screens today, but are also among the most expensive to produce. OLEDs are known for perfect blacks, in which the black on the screen is completely turned off, leaving no sign of a backlight to degrade the image. Like plasma displays, OLEDs are eventually susceptible to burning if left on for too long a period of time, especially if a persistent image is left on screen. However, significant advancements have been made to prevent burn-in on OLEDs in recent years. OLED displays are also capable of being flexible, with recent cell phones being released to accommodate a folding aspect within the screen itself. Thanks for watching. If you like this video, please support the channel by reading the pocketbook it's based on, Colour and Technology, the Beginner's Guide. Check out the description for more information.